More people will come in. We'll wait a little bit more. All right. Guys. Okay. Okay, so while we're waiting, let's just recap what kind of questions we have to answer. How many multiple choice do you guys remember for the AP test? Is it 50 or 60? It's 60 questions. Yeah. Some of the tests that we've been doing, I guess, biology is 50, 60, biology is 60, chemistry is 60, yeah. So multiple choice. So just very quick recap. You have 50% of your grade is on multiple choice, right? No calculator, cannot use calculator for multiple choice. It's crazy, yeah. So you see here, you have 60 questions. Again, half of the test, or an hour and a half. Actually, AP test is more than 3 hours. It's the longer test. So is 50% of the grade. There's no penalty, and you cannot use calculator. Now, the free response, you have an hour and 45 minutes. Crazy. I don't know why they do that. Yeah. Why not 3 hours? They have to put 15 more minutes. So there's 7 questions. That's what we're going over today, right? The first 3 are heavy. They're 10 points each questions. And then 4, 5, 6, 7, they're 4 points each. Okay. So that's kind of the setup for the test. And for the second part, use a graphing calculator, scientific calculator, whatever calculator you want, but there is no calculator on the multiple choice. Yeah. So just recap the format. Okay. So with that in mind, okay, the sample test that we've been practicing, some of them are condensed, so they have like 50 questions. That's why sometimes it's confusing. But 60 multiple choice question, there's no penalty. Hi, Justin. Okay. And let's do this. Yeah. So the general rule is that they will try to combine as many chapters and concepts into one question, like a giant question. So if you read the, sorry, I'm going to sometimes zoom in and zoom out. Okay. So here, if you look at the instruction here, you don't have to actually read it during the test. Okay. So question 1, 2, and 3 are long. So they're 10-point questions that requires 23 minutes each. So they give you about 23 minutes, right? Actually, they give you the whole test, but you can assign about 20 minutes each. They're 10 points each. So 1, 2, and 3, they're 10 points each. That's 30 points already. And question 4, 5, 6, 7 requires about 9 minutes each. So 4, 5, 6, 7, they're 4 points each. So about 9 minutes, okay? So you don't want to pace this. You want to do as fast as you can and save minutes, precious minutes for difficult questions. Sometimes 1, 2, 3 will be so hard, they will delay you to go to question 4, 5, 6. So try to finish them first and come back, okay? Leave enough room on the purple, or is it purple or green? One of those color booklets. That is your response booklet, yeah? You cannot put on your test. You have to put on the response, okay? So leave room so you can come back to it, okay? So big picture first. If you look at this first question, this is question number 1, the big one, right? You see this is acid and base because I see acid icebox. I see a weak acid, acidic acid, dissociating water, right? And I have Ka. So I have equipment, so probably they want you to do dilution or titration and then calculate the pH of stuff, percent dissociation. Easy, right? So we're not done. We also have a titration graph. And you can see this kind of titration graph is a weak acid titrated by a strong base. That's why the pH gradually increases. And we have seen the titration graph. The way to look at the titration graph is that the most vertical region is where you get the equivalence point. And the half equivalence point is the most horizontal when pH changes the least. Okay, so if I were to estimate, it will probably took about 14 mil to become equivalent. And the equivalence point is probably here. So maybe like 9.9, somewhere like that. That's the pH at equivalence point. And if I divide by 14 by half, that would be 7 mil. That would be the amount I need to become half equivalent. So 6 is here, so 7 is probably here, yeah? So 7 mil is half equivalence right here. That is when pH always equal to pKa, right? Okay, so we're gonna answer the question, but this is just the big picture. So you know this is a titration question. So this entire question is on titration. That's it. Question number 1, titration. Number 2, okay? All these are spaces that we can skip right now. And if you look at number 2, just big question, big idea first. I'm looking at this. Hydrogen peroxide is always on AP. Hypochlorite is bleach. If you see hypochlorite, you see hydrogen peroxide is redox. Always, they react by redox reaction, right? And you have to do oxidation number. And I see delta G, delta H, and delta S. The thermodynamics question here, okay? And also equilibrium constant. Remember, if you know delta G, you can find equilibrium constant. You can also find cell potential for electrochem. These 3 things are redundant information. If you know one, mathematically, you can find the other 2. So if you know delta G, you should be able to find equilibrium constant always. Okay, so we'll review that very quickly. And then there's some, this is the setup that produce oxygen, right? So maybe PP RT, gases, stuff like that. And then, yeah, something like this. I didn't read through the question here. So that's number 2. Let's just preview one more and then we get started, okay? So the first 3 is the most scary. If you fail first 3, if you do well in the first 3, oh my goodness, then everything is like easy, right? Okay, so next one is fluid structure. Drawing O3, we memorized it. It's sp2 bent, all right? So double bond, single bond. And then you also have delta H, I see here. I see maybe some kind of kinetics coming up here, okay? Kinetics, 0 first, second order, half-life, rate constant, blah, 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 stuff like that. Okay, yeah, so that's it. Okay, so let's go back. Okay, so this is not a, I don't know, it looks okay so far. Okay, so, all right. So again, you'll be given a whole bunch of constants and equations. So let's begin with this and see how this goes, yeah? Okay. So again, I have to split the screen like this. Sorry, so if it's too small, yeah, okay. I may not, because it's recording, so I may not have to write everything out. So you can just download the recording and fast forward to the part that matter. Okay, so let's look at this. Okay, acetic acid is very common. You always see on AP test. So make sure you know the formula for acetic acid, of course, okay? So ethanoic acid is acetic acid. And you can see this is this is the weak acid icebox, right? The weak acid, acetic acid will donate a proton to water and water become hydronium and you get A-. This is your typical icebox template, right? So you want to find out the equilibrium constant. So that's the goal. Using 2 different experimental procedures. So you want to find out the equilibrium constant. Okay, so the student first asks you to prepare. So you have this acetic acid using a 2 molar standard stock solution. So this is dilution. So A says calculate the volume of the 2 molar stock solution. Look how many sig figs, 4 sig fig questions. So you got to be pretty precise. And here is 4 sig fig for the mil, but 3 sig fig for the molarity. Okay, so this is the dilution. So how much of the stock solution do I need to prepare 100 ml 0.115 molar acetic acid? So that would be M1, V1, M2, V2. So number 1A, okay, we're looking for 1 point. That's it. Okay, so I'm going to put here 1 point. So this way you can add up your own points. Okay, so we're going to do M1, V1 to show work. Always write down the equation before you plug them in. Initial molarity, let's say the stock solution is 2.000 molar. Volume 1 is what I'm looking for, but molarity 2, I want to dilute it down to 0.115, and I want the final volume be 100. But carry out the same sig fig is 100.0 mil. Yeah, okay. I like to put the units here to remind myself I'm working with mil, so my answer is also in mils. Okay, so you just solve for V1. That's it. This would be 3 sig fig because 0.115 has 3 sig fig. So you're gonna get you're gonna get 5.75 mil. 5.75 mil, that's the answer. Okay, so that's 1 point, easy point, yeah? Okay, second part. So this is, that was A1, now is A2. Okay, so what are we doing for A2? A2 says, describe the procedure the student should use to prepare this. So we can type up our procedure, and then I want to use the terms here, the equipment. And by no means you have to use every single equipment, of course, right? So just pick whatever you need. Minimum, some extra, doesn't matter, okay? So what you want to do is you want to use the word to transfer to pipette. Remember, pipette is how you can get stuff out, okay? So it's like that straw pipette, right? You can pipette out, and I need to pipette out 5.75 mil, okay, of the stock acetic acid, right? Solution, okay. And then what, right? Because this is not enough yet, right? So I'm looking at the choices here. What exactly do I need? I need the volumetric flask because this is the best, most accurate instrument to store 100 mil. So you need that. Not graduated cylinder, not beaker. Beaker is like a bucket. You don't want to use any beaker. There's no precision at all. You don't want to use an eyedropper. I don't need an eyedropper. Eyedropper is later when you want to. Your volumetric flask has a marking where you can, if you have this 100 mil volumetric flask, will look like this. Very beautiful instrument. Yeah. And then somewhere here, it will mark 100 mil. So your eyedropper is probably needed when you want to be so precise that you want the bottom of the meniscus to be right at 100 mil mark. That's why you need an eyedropper. So you could use that. And you need distilled water as well, because how do you transfer water to dilute? You need distilled water, okay? And so basically, I need that one. But how do I pipette out 5.75? There's no pipette here. I don't have a pipette. So I would have to use graduated cylinder. Okay, so I take it back. So you have to transfer 5.75 mil using a graduate cylinder, okay? And into a volumetric flask, which is 100 mil volumetric flask that already has some water. And then you transfer it in, right, some water. And then you add more water until the mark. Use an eyedropper if need to. So you need to use pretty much most of it, yeah, this equipment. So let me just type out what we just said, okay? Let me, again, because of my tiny little screen, just work with this. So I'm going to type it out here. Okay, so I can't say pipette out anymore because I was looking for pipette. There is no pipette, so forget about pipette, yeah? So I would say that use graduated cylinder to transfer 5% of the stock solution, right? That would be the, now because the question actually mentioned the 2 mil, I will talk about the 2 mil. So that's the stock solution, the 2 mil, not 2 mil, 2 molar. Bunch of march of zeros. 1, 2, 3, 4. Okay, how many are there? Doesn't matter. Okay, molar stock solution. Yeah, there's 3 of them. Okay, okay, into a 100 mil volumetric flask. Okay, volumetric flask already have some water. That's the, you have to put that, okay? Already with some water. Fill, add more distilled water until mark, okay? On the flask, on volumetric flask, okay? Use eyedropper if need to, right? Okay, so that's usually not necessary right here. Okay, so something like those, yeah. Now, the reason you have to add to the volumetric flask already with some water is just a precaution. We always add acid into water, never the other way. Imagine like oil. Do you add oil into water or water into oil? Which one is unsafe? Will be water to oil is unsafe. Because hot oil, put some water in, it's gonna splatter and boil the water. So it's gonna splatter your eyeballs, right? That's not safe. So you never. So think about oil like acid. You never add water to acid. So you always add. So you always add acid to water. Okay, acid to water. So I'm gonna put it here that acid to water is safe. Acid to water is safe, and then water to acid splatters. Okay, if it's strong acid. Now, in this case, the acid is not strong, so I don't think it will matter if you didn't mention that, but it's okay. Just always remember, you always add acid to water. That's why I already have had some water in there, yeah? Okay, whoops, not that far. I mean, already with some water. Okay, that's just a precaution, practice. So that's just, that's 2 points here. So 1 point is volumetric flask, and the other point is for the rest, okay? So there we go, all right? Okay, next one, so that's 2 points. Okay, so remember to keep track of how many points you have. We're gonna add it together every single question, yeah? And let's look at number 2, using a pH probe. So this is part B, B1, okay? What do you have to do? The student determined that the pH of the acetic acid is 2.92. You haven't even done titration yet. So you cheated, you just put the pH probe in there and then it says 2.92, great. And from here, how do you find the Ka and percent dissociation? That's icebox. There is no titration, so forget about titration. You haven't added a strong base to the weak acid yet. This is just icebox, so that's the only thing you can do. So pH is 2.92, 0.115 molar. So I will show work by actually doing an icebox. So here. So the acetic acid, because they give you the icebox, you just follow the same icebox as the one that they give it to you. Don't come up with your own one, yeah? So make sure you add water because they use the one with water, right? So you get hydronium, okay? And then you get the acetate. So how do I show work? I just show them, if you want to show work, this is how you show work. Okay? If you don't, that is fine too, yeah? So this is 0.115. Water, you don't care, just placeholder, 0, 0, minus x, plus x, plus x, right? So do you see that usually we will be solving for x by setting up Ka is x squared over 0.115. But we are looking for Ka. That is why you're given x in terms of pH, because x is hydronium. So pH is negative log of x. And pH was, what was the pH? 2.92. So the pH was 2.92, and you solve for this. Now, we're close in on the AP test, so I need you to be careful about sig fig. If you log something, you add a sig fig. If you are solving for x right now, you anti-log. If you anti-log, you get rid of a significant figure. So I need to get rid of one significant figure. So my answer will be 2 significant figure. Yeah. So again, you've logged something, you need to add a sig fig. If you anti-log, like what I'm doing right now, you get rid of a sig fig. So this one is 1.2 10 to the negative 3. Okay. 1.2 10 to the negative 3 molar. And now we know what x is. I plug it in to find Ka. Again, the goal for this experiment is to find Ka. So 1.2 10 to the negative 3 quantity squared divided by 0.115. And you can also minus x if you want. You don't need to approximate here, but really this doesn't change your answer at all. So you can solve for x. Again, you can approximate by dropping off the x, but since you're not solving, you should just carry out the x. If you didn't, that is fine. Your answer will not change. I got 1.3 10 to the negative 5. And that is the answer here. Okay, no units for equilibrium constant as always. Here, there are 2 points. You can imagine 1 point for finding the hydrogen and 1 point for the answer. So B1 is 2 points. Okay, let's look at B2. Percent dissociation, 1 point. So that's super easy, right? Percent dissociation has to do with x. X alpha 0.115 dissociated. And because equilibrium constant is less than 1, not a lot of dissociate, right? X is really small. So your percent dissociation, basically B2, is 1 point right here, yeah? Oh, I think I'm lagging. Okay, wow. Okay, well, that's not normal. Okay, sorry about that. Okay, let's see if I can get those back. Okay. Well, that hasn't happened before. Okay, it just disappeared. We'll see. Okay, anyways, so you basically do x divided by the original acid concentration. So that would be x divided by, well, our x was 1.2, right? So x divided by the original concentration, 0.115, and you just times 100%. That is the percent of dissociation for this weak acid. Strong acid will dissociate completely. Only weak acid have this kind of percent dissociation. So if you plug in x as 1.2 10 to the 4 divided by that, we get what percent? We get 1.0%. Why is it 2, not 3 sig fig? Because x was 1.2 10 to the negative 4. Even though the bottom has 3 sig fig, x is 2 sig fig. So when you divide them, your position is limited to 2 sig fig. So 1.0%, not 1%, 1.0%. Okay. All right. So that would be the answer for part B. Again, that's 1 point. Okay. So let's see what we can here, what get cut off. Okay, so percent dissociation here. So let me just write it in. Okay, so this would be 1.0%, right? Okay, looks like I'm still 1.0%. Okay, so it's x divided by 0.115. All right, let me put it back. And let's look at the next one. So that's one way to find Ka, we found it. Now there's another way to find equilibrium constant, okay? Remember we got 1.5, 10 to the negative 5, okay? 1.3, 10 to the negative 5. Another way is to do titration. What does this have to do with titration? Titration, by looking at the half equivalence, guys. Half equivalence point of every single titration, pH is going to equal to pKa. And if you know the pH at half equivalence point, you can solve for equilibrium constant. That's technique number 2. So what is number 1? You stick a probe, pH probe, find the pH, use the pH to find hydrogen, which is x, and use x squared over 0.115. Oops. So again, use the pH probe to find the pH and find the hydrogen concentration and solve for Ka. Second way is to do titration and find the half equivalence point. If you know the pH at half equivalence point, pH at half equivalence is pKa, then you can solve for Ka. That's the second methodology, yeah? Okay, so we're given this titration graph. Let's see what information is needed here. This is important here. Okay, so let's take a look at this. All right, so here's a titration graph, okay? So part C, write a balanced net-on equation between a weak acid, which is acetic acid, and a strong base. I don't care about the sodium, it's neutral. So this is type 2 titration. So how do you write weak acid with strong base, right? So we've done those before. So part C, the weak acid is acetic acid, so HC2H3O2. Strong base is OH minus, and this is not equilibrium, this is BCA. Yeah, this is limiting. And strong base will take away the proton from the weak acid to form water, and the weak acid becomes conjugate base. So that is the answer. So 1 point for knowing how to write this equation. Super easy, yeah? Okay, so C is 1 point. You solve 1 point or no point. Do not put sodium in here because it says net ionic. If you put sodium, it's wrong, right? Okay, part D. They want you to calculate the concentration of sodium hydroxide. That is definition of equivalence. Because we know where the equivalence is right here, right? And I said that equivalence pH is about here. That's when the graph is most vertical. So you must have added 14 mil sodium hydroxide added to become what we call the equivalence point. So this question is based on that. At equivalence point, moles of acid must equal to moles of the base. So it will be molarity of the acid, the volume of the acid, molarity of the base multiplied the volume of the base. And the equation I gave you also taking into account of number of protons. In this case, number of protons is 1. Acetic acid only have 1 acidic protons. The rest of the hydrogens are attached to carbon and they are not acidic. Acidic hydrogen is dissociated, right? So it is 1, so it doesn't matter if you include it. And IB is also 1 because sodium hydroxide carries 1 hydroxide. So it doesn't really matter if you forgot to include that. So I'm just going to plug it in, right? So the question tells me from the chart, I've added 14 mil of the base to become equivalent. What would be the molarity of the sodium hydroxide, right? And my acid, now I'm going to look at my acid portion. The acid is from before. Remember we had 2 molar 10 mil. So you plug in 2 molar 10 mil in here. So I have 2 molar, 2.000 and 10.0 mil, right? Okay, so this is the molarity of the base. So if you multiply it out, okay, what do we get? Yeah, molarity of the base is 1.43 molar. Yeah, it's okay. All right. So you get 2 point. How many points? 2 points here. 1 point for setting up, and 1 point for the answer. Setting up means you're able to find moles of the acid, and understanding that moles of the acid is the moles of the base. So from the moles of the base, 14 mil, you can find the molarity of the sodium hydroxide that is used. Okay, so that is part D. So part D, 2 points for part D. Please add it together. And last part, part E, same question here. Now, how do we find the Ka? So explain. You don't have to actually calculate it, right? It says explain, not calculate, not find the Ka. Just explain how you can estimate the value of the Ka. Well, the key is the half equivalence point we said, right? So you knowing that 14 mil is what is required to become equivalent. So half equivalent would be 7 mil. And by extrapolating from the half equivalence point, we can find the pH, which is the pKa. Let's say the pH is 4.5 equal to pKa. Do you see I can solve for Ka? Will be 10 to the power of negative 4.5, right? That's if you have to calculate it. So we're not calculating it right now. I just explain how can you use the graph, the data, the experiment to find the Ka. All we have to do is type that out, okay? Part E is 1 point for this one, okay? Okay, this is part E. Okay. And always look for the half equivalence. How do you know where the half equivalence is? You find the equivalence of an amount, volume, which is 14 mil here, you divide it by 2. Or you look where the graph is the most horizontal. But that's not a very good method because technically it is not horizontal, it's kind of slanted. So you find equivalent divided by 2. Okay, so find the pH equivalence point. Since pH is equal to pKa at half equivalence point, doesn't matter what kind of titration, yeah? Solve Ka, okay, from there, yeah, that's it. Alrighty, so that is just 1 point for this. So we're done with question number 1. This is a 10-point question. Can you please add up all the points you've received for question number 1 and just put it on the side? So add all the points if you skip it together, okay? All right, okay, you guys got it? Okay, so score the points while we do them so I can just move on, yeah? All right, let's look at the second question. Second question is also 10 points. Okay, let's take a look at that. Okay. Second question has to do with hydrogen peroxide. So one thing every time I see hydrogen peroxide, you might as well memorize this. Okay. So question number 2. So here's the thing about hydrogen peroxide. Hydrogen peroxide has an oxidation number for oxygen that's 1-. Usually oxygen is 2-, but it's 1-. Okay, that's the first thing. Second thing about hydrogen peroxide is its decomposition is super famous. Hydrogen peroxide will decompose to produce water and bunch of oxygen. This is that elephant toothpaste I showed you guys. It's going to release so much oxygen, you put soap in, it just becomes a foam that gushes out due to the pressure buildup. Elephant toothpaste, okay? So oxygen. And also hydrogen peroxide is always first order. Always. They cannot make up something that is they can change facts. So if you see hydrogen peroxide, you know right away it is first order kinematics. Okay, which means the half-life for hydrogen peroxide decomposition, it's 0.693 over K, right? This formula is given. So all these about hydrogen peroxide, and last thing is the Lewis structure. It's bent on both sides, like water on this side bent, sp3 bent. Okay, so and it's polar, of course, and it has hydrogen bonding. So all these things should pop to mind right away. And it's a household disinfectant. You use hydrogen peroxide to kill germs and bugs and not bugs, germs and cuts basically. Okay, so these things are about hydrogen peroxide. Okay, alrighty. So let's look at what the question is. Okay, that doesn't mean this is first order because this is not hydrogen peroxide decomposition. So the question: investigate the relationship between blah 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 and sodium hypochlorite OCl minus is the bleach. It is strong base. Is bleach. The power of bleach is to oxidize stains. When stains are oxidized, they become colorless. All right. So is the reaction redox? Yes, the answer it is redox because all you have to say is that oxidation number changed. And how? So you have to say oxidation number for hydrogen peroxide here, oxygen is 1 minus, but on the right hand side, oxygen here is 0. That's enough. Yeah. So you can use that, or you can use the one in water. It doesn't matter as long as you indicate that the oxidation number somehow changed. Okay. So 2A. All I'm going to show is that yes. So answer the question first. Okay. So in hydrogen peroxide, O is 1 minus. In water, O is 2 minus. In O2, O is 0. Right. So I put 0 in this. So chlorine did not change, did it? Chlorine actually did change as well. So you could use oxygen, you can also say chlorine, because chlorine on the left side is 1 plus, oxygen is 2 minus. And chlorine on the 1 minus is 1 minus, right? So this is an oxidation. And hydrogen peroxide is reduced and it's oxidized. You can have 2 oxidation and 1 reduction. That's fine. You just can't have everything reduction or everything oxidation. You can have 3 oxidation and 1 reduction, 3 oxidation and 2 reduction. Doesn't matter. But you cannot have all oxidation or all reduction. So here we see 2 oxidations with 1 reduction, which is fine. But the point is that it is a redox. So give them the idea, tell them the oxidation number changed. Okay, that's it. 1 point. So can you give yourself either 1 point or no points here? Let's look at part B. So this is thermodynamics now, right? Okay, and to further understand the reaction, the student look up thermodynamic data. Okay, so it said delta G is negative 197. That means spontaneous. Equilibrium constant is greater than 1, right? Every time delta G is negative, the first thing pops to mind is that the reaction is spontaneous. And equilibrium constant must be greater than 1, Plotter's favor. They always go together. And you also look at this one, delta S is positive, more disorder. And that makes sense because if you look at your reactant, there's 0 gas. And if you look at the product, there's 1 gas. So you're producing gases, creating greater entropy. Alrighty. So the question is part B. They want you to use that information and this equation, delta G equal to delta H minus temperature delta S, to find out what delta H is. So when we plug this in, often people know the equation, but they plugged in incorrectly. So if I plug in 197, solving for delta H, temperature is 298 if you're not told, and I plug in 144. What did I do wrong here? Right? Because if I do this, I get wrong answer. Well, the reason is because of delta S is always given in joules, and delta G is in kilojoules. You cannot do joules and kilojoules, so you would have to make that adjustment. So usually I just convert 144 into kilojoules by dividing 1,000. So if you don't do that, you're not going to get the right answer. Okay, so it's something very simple, but we always make mistakes on. And so for delta H, for the reaction, don't make a mistake on this one, right? And if you solve for it, your delta H is negative 154. If you don't put units, you get wrong. So 154 is kilojoules, and they always put per mole of reaction. It is the same as just negative 154 kilojoules. But per mole of reaction is always there. So this means that I have an exothermic reaction that produces heat, and that produces more disorder because S is positive. So I have scenario number 1. I have an exothermic reaction that produces more disorder. So this is always spontaneous, regardless the temperature. Yeah. So an exothermic reaction that produces more disorder, 2 driving forces, both making G negative, is always spontaneous. All right. So that is the answer for part B. How many points for part B? 1 point for part B. So please give yourself 1 point or no point for part B. Let's look at part C. Part C is the interpretation what delta H is. We got negative answer, so the reaction is exothermic, right? So does the temperature inside increase, decrease, or remain the same as reaction progresses? Well, if it's releasing heat, it's going to heat up, so temperature increases because the reaction is exothermic. That's it. You can't just say temperature increase, okay? You have to say reaction release heat is exo. So increases. Don't abbreviate on the test. I'm abbreviating right now, yeah? Because reaction has negative delta G, delta H, I'm sorry, and is exothermic. That's the key word they want to hear. So relate delta H to exothermic. You can't just say delta H is negative. I don't think that's good enough. Relate the negative delta H to exothermic reaction. Heat is released. All right, that's obviously just 1 point. Not a lot of point here. Let's look at part D. Calculate equilibrium constant. So once again, if you know G, you can always find equilibrium constant using this equation. Negative RT natural log of K. So this equation is given on the test, on the free response part in the equation sheet, right? So delta G equal to negative RT ln K. Now, when we plug this in, we also plug in wrong, incorrectly. So for example, delta G was negative 197 and R is 8.314. Do not plug in 0.0821 and temperature is 298 and this is natural log of K. If I did this, I would have gotten the wrong answer. Once again, this is in kilojoules. So your R have to divide it by 1,000 to modify it to kilojoules. So don't forget to do that. If you use kilojoules, R must be divided by 1,000. So this equilibrium constant will be a very big number because G is super negative. It's e to the power of 78.5. That's huge. So it's about 3 times 10 to the, was it a 34 or something? Okay. Anyway, it's bigger than 1. It's definitely spontaneous. Yeah. Products are favored. You get very little, if any, reactant remain. So this is simple calculation, 1 point with calculation. Yeah. All right. Okay. Let's look at the next one. So we're done with the first part. So now, even though this is still the second question, they're switching to another part. All right. So you can see this equation. This is actually how you have to carry out if you do the actual reaction. Let's take a look at this for a sec. Yeah. So this is telling us right here. Okay. The student, remember the reaction is to put hydrogen peroxide. Okay. Which is here. Okay. And you mix with bleach, sodium hypochlorite. And the bubble is oxygen. So the oxygen will be collected here. So this is the downward displacement of water. You can see that water is being pushed down. So in here, container, guys, what are the 2 gases that is collected? Will be oxygen, obviously, right? Because the reaction produces oxygen, and also water because it's collected over water. All right, so that's what the experiment is about. So the student decide to produce 40 mils of oxygen at this pressure and temperature, PV equals RT, using the reaction. All right. The student had equipment below. The student set up a 200 ml LMIR flask. That's this. This is the flask. Okay, LMIR flask is like a beaker. Is not accurate at all. No precision there. With a 1-hole stopper, so you can see that the stopper allows the things to come down. Right. The flask is connected to 50 ml collection tube right here, initially filled with water. So this is the setup. Downward displacement of water. Very basic setup, okay? Let's see what the question wants. Calculate the volume of 0.8 molar hydrogen peroxide that you should add to access this, produce this. Okay, this is stoichiometry. So you just need to write down the equation. So let me put that here, part E. Okay, part E is how many points? Let's see. Part E is 2 points, okay? So this is gas stoichiometry. It's not hard, okay? So let's look at the equation. They gave us hydrogen peroxide and sodium hypochlorite. So just go back to the equation here, okay? So OCl minus produces water, Cl minus, and you have O2. It is already balanced, all right? And then because it's stoichiometry, you write down what you're given and what you're looking for. So the question is this: what is the volume of 0.8 molar hydrogen peroxide? So I'm looking for volume, liters or mil, doesn't matter. You have 0.800 molar hydrogen peroxide. You see, I write down the information right beneath it, so I know this belongs to hydrogen peroxide. And I have access. I don't care about access, so that's useless now, okay? And 40 ml of oxygen, so this is what's collected. 40.0, carry out the right sig fig. You're collecting at 0.988 ATM and 298 Kelvin. Does that make sense? Okay. So this would be the amount of oxygen you need. So how do I do this? So how do I know which side do I go? Well, you have to go from here because you have question mark on the other side and you got to go this way. So use PV versus RT to find moles of oxygen. Mole ratio says 1:1 to find moles of hydrogen peroxide. Moles and molarity to find volume. Okay, so that's what I'm going to do. I'm going to show work by writing down PV versus RT to find the moles of oxygen first. So the pressure of oxygen you need is 0.988. This is just pure oxygen. There's no water there. And the volume, if you put 40.0, you get wrong answer. You have to be in liters. So you divide it by 1,000. And then you're looking for moles of oxygen. R is 0.0821. It's not 8.314 because this has 2 ATM. And temperature, you're told what the temperature is. It says 298 Kelvin, right? So it has to be in Kelvin, never degrees Celsius. If you're not sure, put Kelvin always. And you can find moles of oxygen, that's 1 point. And the moles of oxygen here is 0.0. So 1.62, 10 to the negative 3. Okay, 1.62, 10 to the negative 3 moles of oxygen. And it is 3 sig fig because the 0.988 or 40.0, right? So now I have the moles of oxygen. I'll do the mole ratio to find moles of hydrogen peroxide and then volume. So you show work, dimension analysis, 1.62, 10 to the negative 3 moles of O2. The mole ratio from the balance equation is 1:1. So 1 mole of O2 to 1 mole of hydrogen peroxide. Okay, so you're almost there. You want volume in liters. So you need to use the molarity. So the molarity is 0.8. So you put 0.8 moles on the bottom to 1 liter. And that is the answer. You can see from the file will be in liter. The second question, you're going to end up how many liters? It's 2.02, 10 to the negative 3. So 2.02 times 10 to the negative 3 liters or 2.02 milliliters. So 2 points, 1 for PV versus RT, 1 for the final answer. Your final answer has to be 3 sig fig. You cannot put 2.0, 10 to the negative 3. That's wrong because everything here has 3 sig fig. Your answer has to be 3 significant figure. So 2 points for part E, okay, and part G now. Last part. Let's see what else. See part. Oh, okay. So I guess we're not done. Part F, A, B, C, D, E, F, G. Look how long it is, right? So F. So the student added amount of hydrogen peroxide. Remember that's the burette. You drain hydrogen peroxide into the bleach on the bottom, the Erlenmeyer flask, producing oxygen. So this is what he is reading, okay? So the hydrogen peroxide. Okay, so again, I'm gonna draw the burette out. So this is the, whoa, sorry, it's hard to draw a straight line. Okay, so this is the burette. Okay, and what was in the burette again? It was hydrogen peroxide. Okay, and you add it to this Erlenmeyer flask. I'm just gonna draw a beaker. Okay, and what's in here is OCl minus. All right, so this is what you're adding. Okay, and this is what you're reading. The student added amounts of hydrogen peroxide to access this. However, producing 40 mil. Oh, okay, actually, this is the volume of the oxygen produced. My bad. Yeah. So this is the pipette on this side. This is the oxygen. Okay, so that's what we're reading here. So you got to read the bottom of the meniscus. Okay, so bottom of the meniscus right here. So the question is, based on the diagram, what volume of the gas is produced? Remember, bottom is water here. So your gas is in here. 0 is at the top. So you're reading from 0 mil, and this is past 30. I see past 35. So how many sig fig do I carry this out? Okay. So the way you do this is that you know this long one here is 35. And this looks like it's 36 and 37. So it's between 36 and 37. So you would have to write down 35. Sorry, not 35. It's between 36 and 37, right? So you have to write down 36 point, let's say you think it's 0.5, because you are sure it's 36 and 37, but you're not sure whether it's 34, 36.4, 30. This is the uncertainty here, right? So you have to report this to 3 significant figures. So the answer is that, okay, 36.5. They will take 36.6, 36.4, they will even take 36.7 or 36.3. So they take a bunch of them, but you need 3 sig fig. Otherwise it's wrong. Okay, so that's the answer. All right, so 1 point for F1. Okay, 1 point for F1. And the common sense to put down 36.5 mil. And you need at least 3 significant figures. And so that's how much oxygen is produced. All right, the question is, assuming all the gas is O2, okay, what is the percent of yield? So your percent yield of O2 is how much you actually produce, and how much in theory, right? Theoretical yield, and convert that into percent. So what we're reading here is actually the actual yield, 36.5. That's your actual yield. You can use mil, because mil is proportional to the amount of oxygen, right? But what are you supposed to get? You're supposed to get 40. You're told right here in the part F, you're supposed to get 40 mil. You only got 36.5. Well, that is not 100% yield. So you just divide it by 40.0, and then you convert that to 100%. So this is also 3 significant figures. So the answer is 91.3%. That is the yield. Okay, it's a pretty good yield for the experiment. So 1 point for F2 as well. So 1 point for F1, 1 point for F2, and then next one is 1 point for F3. Yeah. So F3 is the assumption that all the gas in the tube is oxygen. Is that a correct assumption? The answer is no, because you're collecting this over water. Water will also vaporize. So that was what we were trying to draw in the very beginning. When you do this downward displacement of water, I didn't draw it out. Yeah, right here. So there's oxygen, there's also water vapor, because you're collecting this over water. So there's actually both water and oxygen. So the answer is no. There's also water vapor. All right, that's 1 point for F3. Let's look at part G. To account for the percent yield being less than 100%. So how come you don't get 100%, right? The student claimed that the reaction reached equilibrium before the expected amount of O2 was produced. So the student is arguing, you reach equilibrium before you produce 100%. So you reach equilibrium at 90%, 91%, right? Now the question will give you a clue. Considering your answer to part D, do you agree or not? What is part D? Part D here is asking for the equilibrium constant. Your equilibrium constant is huge. That means it essentially goes to completion. So arguing that a reach equilibrium is wrong, is incorrect. You don't agree with what the student is saying. So part D is your K. So equilibrium constant is greater than 1 and is huge, right? It was like 10 to the 30 something power, right? Means that the reaction goes to essentially to completion, and does not reach equilibrium, So that I have to say no or something like that. Let me see what that says. So do you agree? So we disagree. So you have to say that first, okay? So you disagree with the student because the equilibrium constant is greater than 1, huge, right? I would actually write down what it is. I forgot what the equilibrium constant was. It was like e to the 78 power or something, yeah? But anyways, it's huge, okay? All right, so that is now 10 points. So 1 point for the last one. Could you please add up all your points for part 2 and give yourself a sub-score, please? Okay, let's move on to part 3. Okay, you notice that there's always Lewis structure, probably resonance question. They're very common on the test, yeah? Okay, so let's look at part 3. Again, if you look at ozone, O3, you should right away know that O3 is called ozone, okay? Oxidation number is 0, it's free element by itself, right? Neutral, no charge. And the Lewis structure is double bond on one side and single bond on the other side is bent, like that, okay? It's sp2 because there's 3 electron domain about the central oxygen. It is sp2 bent. However, this is non-polar. Usually bent is polar, but because all the atoms are identical, you cannot be non-polar. Electron must be shared evenly. Even though the shape is asymmetrical, not symmetrical, there is no dipole to be polar, so it's actually non-polar. Okay, so the question part A3. They tell you the clue how to draw this. It says that oxygen, O3, has a central oxygen bonded to 2 outer that is not bonded to each other, so it's not circle. So don't draw like a circle. Things don't like to be circle, right? They give you that clue, so forget about circle. Draw the Lewis structure and all the resonance. So I need to draw the resonance as well. There's only 2 resonance structure. You draw resonance by using double arrow and just move the double bond around, that's it. So now this would be the double bond on the left side and this is on the right side and everything else is identical, yeah? Okay, so that's the answer. So 50%, the double bond is going to be on the left, 50% on the right. The double bond is the pi bond. The single bond is always the sigma bond. Additional ones are the pi bond. So 3A, because you got to draw resonance, is 2 points. Please give yourself 2 points. If you only draw 1 structure, just 1 point. Yeah? Okay. Part B, make sure you always read the question. A lot of Lewis structure, people forgot about resonance when they ask you for it. All right, so part B is shape, where we know the shape. So look at the central carbon. It has 3 electron domain, must be sp2 hybridized. It is bent. So do I need to do any more, part B? What is the shape? No, just bent. You get 1 point for saying bent. They didn't even ask for the hybridization. So you just say bent. Angular, V-shape, bent, doesn't matter. Part C? Okay, so part C is a famous equation. Yeah, ozone can turn into oxygen, vice versa. So here I see 2 ozone gases, okay? And this is a single arrow, so I don't assume this is equilibrium. This is 3O2 gas. So I look at the gases, it's more chaotic. I have an exothermic reaction that produces more disorder. Delta S is positive. So this must be spontaneous all the time, right? Okay, so this is exothermic. So the question wants you to do this. Let's talk about bond energy, right? Bond energy is one of those 5 ways to find delta H. If you're using the bond energy, the delta H is the sum of all the bonds on the left side, the reactant side, that are broken, minus all the bond energy or bond enthalpies on the right side, the product side, all the bonds that are formed by the reaction. So it's the left side minus right side, okay? So the bond energy, so when you give them bond energy or bond enthalpy is this, okay? So that's that one. So it has to do with this. And it's exothermic. So the question is, okay, if you read the question here, let me just highlight them. So the bond energy of OO in O2 is 498. They give you the one in oxygen. Based on enthalpy of the reaction, so based on the delta H, negative 285. What is the average bond energy of the oxygen bonding O3, the average one? The reason it says average because if you look at O3, one is double bond, one is single bond, but don't they resonate? They average to about 1.5. Not 2, not 1, not double or single, but about 1.5 bond between oxygen and oxygen. So I'm just plugging this formula. That's all they want you to do. You see my left side is ozone. My delta H is negative 285. So what are all the bonds on the left? I have 2 ozone, right? Do you see that each ozone has 2 bonds? So I'm going to call each one X kilojoules per mole. So if I have 2 of them, wouldn't that be 2 times 2? That's actually 4 X on the left side. 2 ozone molecule, every ozone molecule has 2 X's. There's 2 ozones, so that's 4 X's. That is all the bonds on the left side. Minus 3 O2. So that would be 3 times the bond energy for O2, which is given right here as 498 kilojoules per mole. So you're given that. So I just plug it in. This is 498, right? So all the bonds on the left, there's 4 OO single bonding ozone, minus all the bonds on the right, there's 3 double bonded oxygen. And you solve for X. That is the answer. So it's recognizing which equation to use, plug it in, and you get your answer. So make sure you don't get the math incorrectly when you solve for X. Okay. Here, let's see what we get. We get X equal to 302. And the unit is kilojoules per mole of those bonds. And that's the answer. Okay, 302. So this is 2 points. Yeah. Okay, 2 points. One for the answer and one for the equation setup. So 2 points. If you only put the answer, then there's only 1 point. So make sure you set up the equation, plug it in properly. Okay. So that would be it. So another way is so can you give yourself 2 points here? Okay, it's hard to earn those points. Yeah. Okay. Now, next one. So we continuation here. So this is now something a little bit different. Now it's saying that ozone can react with HSO3 minus. Now, first thing pop to mind, if you look at this HSO3 minus, it can donate a proton as an acid. It can also accept a proton as a base. So HSO3 minus can donate, can also accept hydrogens. But that's nothing to do with acid and base. We're already done with acid and base. Okay. So here's the equation that's given. Over in the equation. The question is, a solution is prepared with the initial, so it says my connection is unstable, so I might get cut off. Okay. All right. So let's take a look at this. So we're given the initial concentration as this, for this one, okay? For one of the reactant. It's 6.4 10 to the negative 4. Not a lot, okay? But it says it's much, much larger than ozone. 1 times 10 to the negative 5. So that's 40 times larger, 10 times larger or something, yeah? Okay? So it says it's much larger. Okay, that is a weird way to say that HSO4 minus so large, don't worry about it changing. It's constant. This will be constant, okay? So when the reaction proceeds, this is going to be rather constant. It's not going to decrease much. Oxygen, ozone will decrease quite a bit, okay? That's what they're trying to say. So anyway, let's ignore all that. And then the concentration of O3 is proceeding. You see that the concentration versus time drops. It's not a straight line. So this cannot be zero order, right? It cannot be zero. This is actually first order. And I know this is first order because I look at how it drops. If I start with 1 times 10 to the negative 5, it becomes half in 0.01 seconds. And then it halves again in another 0.01 seconds. This decomposition or reaction has constant half-life. It becomes 50%, this is 100%, and becomes 25% in fixed amount of time. Only first order kinematics have constant half-life and will decay like a radioactive decay, like what we're seeing here. So this is definitely first order. They don't have to plot natural log, okay? I know if you do natural log of ozone versus time, you're gonna get a straight line where the slope is equal to k, but we're not talking about that because I don't have that graph. But the way it decays is first order kinematics. So it is most common reaction mechanism that you might see. So part D is asking you questions about that, okay? Consider the rate law. So do you see they give you first order? K1, O3 to the first power. Based on the graph, what is the half-life? So if this is first order based on the graph, the half-life is, and I'm just looking at the chart, okay, no formula here. It is 0.01 seconds, because the time is second. Every 0.01 seconds, the concentration of ozone is halved. Okay, that's why the half-life is eyeball. You just look at the graph, you know what the half-life is. Okay, and if you know what half-life is, the next question they will ask you to find rate constant, because first order, the half-life is always 0.693, which is natural log of 2 divided by the rate constant. You see that? Okay, they're going to ask you for rate constant. So let's see what it is. Part D2, determine the value of the rate constant including units. So there, yeah, okay. So I just solved for it. So the half-life, I plug in 0.01. You can use calculator, don't forget, yeah. So you don't have to do this in your head. Okay, but this will be 69.3. And what is the unit for half-life? If you don't have unit, it is wrong answer. You get 1 point for the answer and 1 point for the unit. So 2 points for part 2, 1 point for the half-life. So the unit is 1 point, okay? So the value is 1 point, the unit is 1 point. The unit is always 1 over time for first order. So 1 over second. For the first order kinematics, the unit for rate constant is always 1 over time. If you don't remember, you can solve for the unit by plugging rate equal to k times a to the first power. Rate is molarity per second, and you solve for k, this is molarity first power. You see molarity will cancel, so unit is 1 over second, always. Okay, that's how you get 1 over second. You can just memorize it. So it is 2 points, 1 for 69.3 and 1 for the unit. And part 3, okay? So consider the relative concentrations of the reactant. Now remember, we are told that HSO3 1 minus is a huge concentration compared to O3, okay? Why the data is also consistent with this rate law. Okay, so this is a little weird, and then let me just read the question again. So considering the relative concentration of the reactant, we are told O3 is little, HSO3 minus is huge relatively. Briefly explain why the data in the graph are also consistent with this rate law. So look at this rate law. They use K2 now, not K1, okay? Because it's a different reaction mechanism. So they say, how is this also true? This is also true because why? Well, because the assumption, right? If you look at this one, is how many points? Yeah, it's 1 point. Yeah, so this is 1 point also. So because of the assumption, what was the assumption? Since HSO3 minus molarity is a lot greater than O3 and essentially remain constant and remains constant. Okay, so that means it is not going to change. So do you see that if this is constant, I can just divide this over here, not divide it over here. I mean, I move it over, not divide. So I could have written rate is equal to K2. Again, that's all you need for point. I'm just explaining a little bit more in detail. So you can move these two together right here. That, and this is times by O3 to the first power. And this whole thing here, guys, is K1. Okay, this is just another constant. This whole thing is K1. So do you see your rate law is equivalent, is K1 times O3 to the first power. Because K2 times this concentration, which is essentially not changing because it's so large, that is essentially K1. So this is also true. So this is the reason why when one of the reactant has so much concentration, it doesn't change, it becomes a constant. So it is essentially first order with respect to O3 and is not dependent on HSO3 minus. But to answer the question, you just have to say that since concentration of HSO3 minus is a lot bigger and remain constant, that's the answer. Okay, so that's 1 point there. So the last part 4. Okay, what is part 4? Describe an experimental procedure that could provide evidence to support the rate law in D3. So that is first order, right? So this procedure will be like this. Remember, we actually seen question like this where you do different trial 1, trial 2, or experiment 1, experiment 2, and experiment 3, right? What do? You keep one of the reactants same concentration, and let's say you double concentration here, and you figure out the rate. If the rate also doubles, then this must be first order, right? We've done these before. You keep the concentration of one of the reactant constant, double the O3 concentration. If rate double, is first order. If rate quadruple, is second order. If rate remain the same, then it's a 0th order, right? We've done these before. So briefly describe an experiment to support the rate law on the above, right? Okay, so does that make sense? So maybe I'll type it out, right? So you can do just type it out, okay? And then again, this is just 1 point. But to earn that 1 point, you really have to be thorough and answer the question. Kind of annoying. And then don't stress out and spend 5 minutes on this part. You're gonna run out of time with the other questions. So it is question like this that sometimes feels a little weird. Do I need to really spend 5 minutes on one single lousy point when the chances of getting them correct is not very high? No, you just move on, okay? So again, the question says an experiment that provide evidence to support that it is that. Okay, so you prepare HO3 minus, and it's just a lot of writing is annoying, yeah? Okay, solution with, I'm just gonna prepare 0.1 molar, okay? I'm using an example. Okay, so 0.1 molar, okay? Yeah, okay? Okay, all right. Then I will do, I will double O3 and see if the rate doubles. If the rate doubles, then reaction is first order with respect to O3. And then prepare 0.1 molar O3. Okay. Then you double the other one, right? Double concentration or double HSO3 minus concentration, right? To see if the rate also double, right? If the rate doubles, then reaction, same thing, is first order with respect to HSO3 minus. If the rate is constant, then reaction is zero order with respect to HS. So you get the idea. So because we are trying to verify is the first order. So I gotta double oxygen while holding HSO3 minus. That's what I would say, but I'm not typing that out. And I do the other one. I would keep O3 constant, double HSO3, and to see what happened to the rate, right? If they both doubled, if the rate doubles when both are doubled, then the first order with respect to them. So it'll be something along those lines. So this one is just 1 point. So please give yourself 1 point. You hear something similar to that. If you don't, just no point. Can you please add up the total number of points? Okay, for this one. Okay. So now we are at the short response, which is a lot faster now. And then I think they're a lot easier, but there's also some weird ones. Sometimes you can get electrochem, the entire electrochem. Sometimes you get stoichiometry. Sometimes you get weird gases. So you never know what they're going to give you. Sometimes you get intermolecular forces. So let's look at number 4. Okay. So this one, because it's a lot shorter, I'm just going to copy and paste onto our whiteboard and then go from there. So do you see this one here? First of all, oh, whoops, let me take this away. Look at this one. You see these two molecules here. Glycerol on the left side has capacity for hydrogen bonding. That is very polar, right? Hydrogen bonding is one of the strongest intermolecular force. However, on the right side, this trichloropropane right here has no capacity for hydrogen bond. So you know that the intermolecular force for glycerol must be stronger. And that's why it has higher boiling point. That's totally true, right? Both are polar because both are asymmetrical, but glycerol exhibit hydrogen bonding. It also has dipole-dipole forces, and it also has London dispersion, right? But the most significant one is hydrogen bonding, where the other one has dipole-dipole forces and London dispersion, and overall has weaker intermolecular forces than that of the glycerol. Okay, so we already know this. The boiling point verified that this is indeed correct. Okay, so let's look at the question. Yeah, so based on this, let me take a picture now, and then we'll move on to our whiteboard for discussion here. Okay, if you read the question, they're not isomers because obviously the molar mass is different, right? And I see calorimetry question here too. So this is a quick jab at your knowledge for calorimetry, Lewis structure, intermolecular force. Nothing very creative here. So let's see what I want. Okay, so let me get this guy a little bit bigger so we can see. Okay, so part A. Let's look at part A. Which compound? Identify all, and you got to be careful. They want all of them. So you can't just say hydrogen bonding. You also have to include dipole-dipole dispersion. Present in liquid. Explain why glycerol has higher melting point in terms of the relative strengths of all the intermolecular forces. I think we answered that already, right? Point. Okay. So 2 points here. So to write down, identify, so you don't have to explain. So hydrogen bonding. And on the test, don't abbreviate. So dipole-dipole forces and London dispersion forces. Yeah. On the test, spell it out. Okay. And then the other one is that trichloro, 3-chloropropane. Propane is single bonded carbons. So trichloropropane And this one is just dipole interaction and also London dispersion force. And explain why. Well, you want to say that glycerol exhibit hydrogen bonding and the overall intermolecular force is greater. Okay. So this one exhibits hydrogen bonding and has stronger overall, again, don't abbreviate, intermolecular forces than trichloropropan. Okay, that is why it has stronger intermolecular force. Now, I gave you about 5 or 6 things to talk about whenever you talk about intermolecular force. Let me just review that very quickly, yeah? But that is enough to earn 2 points. One is identify the forces. One is basically explain why glycerol has stronger intermolecular force. I gave you this before, guys. Stronger the intermolecular force, the stronger the intermolecular force. What are the 6 or 5 consequences? Number 1, the higher the melting boiling point, right? So that's what we're using. So we're repeating this. You've seen it so many times. And also higher the heat of fusion, the energy needed to melt, because melting is breaking intermolecular force. Heat of vaporization, the energy needed to vaporize, because to vaporize, you also have to break intermolecular force. The higher the surface tension, right? Surface tension of water, for example, is trillions of hydrogen bonding smacking you. So higher the surface tension. That's why water coils into a bead instead of smears out. Higher the viscosity. So harder to move about, more viscous, more thick. And the only thing that's lower is the vapor pressure. The one that has a stronger intermolecular force is harder to vaporize. Lower the vapor pressure. Just means harder to vaporize, right? Intermolecular force is pulling the water back. Kinetic energy is helping water to escape. So number 6 would be lower the volatility. Volatility is same as vapor pressure. High vapor pressure, more volatile, easier to vaporize. Low vapor pressure means less volatile, harder to vaporize. So those are the intermolecular force consequences, right? You'll for sure see them, so make sure you know how to use them. Now, part B, we're going for 2 points for part B. 2 points for A, 2 points for B. Remember, it's 4 points. Okay, so this looks like it's calorimetry. So here we have glycerol. They tell you the molar mass. You don't have to add them. Has been suggested for use as an alternative fuel. Well, with the Russian war, Ukraine, right? Energy crisis we're in. So we are finding all sorts of alternative energy, right? So maybe glycerol. So the question is enthalpy of combustion. That means if you burn glycerol is negative 1654. 1 mass of glycerol will need to be burned to produce 5 grams of water to heat up 500 grams of water from this to this. Okay? So how do we do this? Okay? All right. So the answer is this. The Q of the reaction, which is the combustion, must be heat absorbed by water, isn't it? Heat lost by the combustion, released by combustion is heat gained by water. Okay, I know what the heat gained by water is because that would be MC delta T for water. I have 500.0. Carry out the sig fig, okay? So don't put 500. It says 500.0. Put down 500.0. The specific capacity for water is 4.184 is given. And the change in temperature is 100 minus 20. Now, some people just put 80. Is that correct? If you put 80, they can mark you off. Because when you subtract 100 from 20 from 100, it's not 80. It's 80.0. So you got to carry out to 1 decimal point. So you cannot put 80. Make sure you put 80.0. That determines that you need 3 sig fig here. So this heat must come from burning, right? So I'm just going to find this first, okay? So if I were to just press equal sign for calculator, I will get 167000. 167,000 joules or 167 kilojoules must be released. But that's not what the question wants. The question wants that, well, I have to get glycerol, right? So how many grams of glycerol must I burn? So you just do a basic stoichiometry or dimensional analysis. If you want 167 kilojoules from glycerol, and glycerol has 1654 kilojoules per mole, that's what you have to use right here. 1,654 kilojoules requires 1 mole of glycerol. That will give you how many moles of glycerol you must burn to produce 167 kilojoules. But you don't want moles, you want grams, so you just use molar mass. 1 mole of glycerol is 92.09 grams. And that's the answer. In grams of glycerol that must be burned, that is needed to burn, to release 167 kilojoules, to raise 500 grams of water by 80 degrees Celsius. That's kind of how you connect everything together. So super easy here. So the answer is 9.3. 9.3. I can't read this, but 9.3 something. Yeah. Let me. I think when you hit 40 years old, your eyesight starts to degenerate. It's very stupid. Okay. But I'm beyond 40. I'm 45 years old. 9.30. When I was you guys' age, I would look at people who are 40 some years old, like old uncle, scary old uncle. I don't feel like an old uncle. Okay, but this is 9.30. You got to carry out to 360. Okay, so that's 2 points. Of course, 1 for calculating 167 and 1 for your final answer, right? So 2 points. So can you give yourself a total of a maximum of 4 points here for A and B. That's it. Let's move on. Number 5. Okay, see, that's a calorimetry, intermolecular force. Yeah. What else have we not done? Electrochem. So there it is, right here. So this is a quick jab at electrochem. Sometimes electrochem is question number 1, right? We did that before. Question number 1, 10 points on electrochem. And then, okay, but this one is 4 points. All right. So you never know, but so you just try to do as many variations as you can. Let's look at question number 5. Again, this is a 4-point question. Okay, let's see what we give it. Okay, now by convention, when you do those electrochem stuff, okay, they usually will give you all the equation you need. Like this one, guys. If you look at the first equation, note it says this is the overall reaction. So that means if you write down the oxidation and reduction, you're gonna supposed to add to this one. And they give you the cathode. So review. Oxidation occurs on anode, reduction occurs on cathode. You have to memorize it, right? So we said the way to memorize like an ox and red cat, right? Okay, so cathode is where reduction happens, so red cat, and an ox, like oxidation, is on anode. Okay, so you have to memorize it. So that's it. So do you see you can use Hess's law? You can find out the anode half reaction because they give you the cathode one. So you can find anode, you can use Hess's law. They have to add up to the overall reaction, right? So this is a play on Hess's law. Again, oxidation half, reduction half, the anode and cathode has to add up to the overall. Isn't this Hess's law? Okay, so let's look at this. Equation above represents reaction associated with lead storage battery. That's the most traditional way to store energy. The lead battery is what we found in the car. The first is the overall reaction that occurs as battery produces electrical current. The second is the half reaction. So anyway, let's just regurgitate what we just said. So part A has nothing to do with anything, just find the oxidation number. So sulfur. If I look at the sulfur before, it's 6+. Okay. And the sulfur after is also 6+. Okay. So how do you know sulfur is 6+? So you need to review oxidation state. Okay, O is 2 minus, except in peroxide, it's 1 minus. Hydrogen is 1 plus each, right? So do you see sulfur must be 6 plus, so that add up to 1. So 2 minus times 4 is 8 minus. And hydrogen is 1 plus, that would be 7 minus. Sulfur is 6 plus, so you add up to the overall 1 minus charge. So you have to know that, right? So whether you look at before and after, it doesn't matter. Sulfur did not change oxidation state. It remained at 6 plus. Okay? So the answer is 6 plus. 1 point for that. Write the equation for the half reaction at the end node. So that's Hess's law. Okay? Hess's law. So how do we do that, right? To show work, you got to show some kind of Hess's law for your understanding. So I'm going to try to show that the cathode and anode adds up. So P, so this is the cathode. I'm just repeating them, okay? Plus 3, I'm not going to put plus because it's very messy, yeah? So I'm going to put 3H plus HSO4 minus 2 electron, okay? And that will produce PbSO4 and also 2H2O. So I need to add another one so that I get the overall. I'm going to put the overall on the bottom. And you can just see what is missing and you get the answer. Okay, so let's look overall. I have Pb and Pb2O3. So I have Pb in the overall. I also have PbO2. And I'm okay. Let me use the same color. I'm sorry. Okay, Pb, and I have PbO2. I have 2H plus, and I have 2HSO4 minus. And I try to line up as much as I can with the equal arrow sign. And this is 2 PbSO4 and 2 water. So you just see what is missing. For example, I need Pb. So I know it has to have Pb on the left side, okay? And PbO2 I already have. And does that make sense? Okay. And also, what else do you have? Do you see the H plus? I need to have 1 H plus on the right, because 1 H plus on the right will have to cancel the 3 H pluses on the left to give you 2 H pluses on the left. So I know that's where H plus has to be. Again, I have to put 1 H plus on the right to cancel out the 3 H pluses on the left so that you have 2 H pluses on the left. So I know that. And I have to have HSO4. I need one more because look at my overall has 2 HSO4 minus. So I need to have one more HSO4. Do you see that? Okay. All right. And then what else? And on the right hand side, I need PbSO4 because overall reaction has 2 PbSO4s. And I need to have 2 electrons on the right hand side to cancel. So like a puzzle pieces, you see now the 2 reactions indeed adds up to the overall, right? Okay, so double check, right? So do they add up to the overall? Yeah, the hydrogens cancel to 2. PbO2, Pb, yeah. Electron cancel, yep. I have 2 HSO4 minus, yes. And I have PbSO4, Pbs, so 2 PbSO4 and 2 water. Yep, that's it. So you just got the right answer. So the answer is this one in green, yeah? This is the oxidation because this is the anode, okay? This is the oxidation. This is a reduction. Reduction is cathode, oxidation is anode. That's your answer. So you only get 1 point for this one, okay? So 1 point for part A, 1 point for part B. Last one, it is stoichiometry. Has nothing to do with anything else. Last one is stoichiometry. So you want to produce, okay, you want to regenerate 100 grams of Pb, that's what's given, using a current of 5 ampere. So now 5 ampere means 5 coulombs per second. You have to know that. You also need to know Faraday's constant. Faraday's constant is 96485. It's given on the test. Coulombs carried by 1 mole of electron. So this is give both of these. You need to know the current, you need to know Faraday's constant, and you need the reaction, okay, the half reaction, okay? So with those 3 things, you can do a question like C. So let's do it. First of all, you need to look at what you're given. 100 grams of lead, you need to know which equation to use. There's 3 equations. dude, which one do I use, right? So if you read the question, calculate the time required to generate 100 grams of lead. It doesn't matter which one you want, but you should use the oxidation one because it connects lead to electron. So my half reaction is the answer from part B. Because there's lead, there's also electron. I'm going to write part B out. Pb SO4 minus, give you H plus, PbSO4, and 2 electron. I just care about Pb and moles of electron, okay? So my stoichiometry begins with 100 grams of lead. My goal is to find out time in seconds. So look at the dimension analysis, will work out nicely. So grams of lead, you got to convert to moles of lead, molar mass. Once you have moles of lead, use the balanced equation. 1 mole of lead to 2 mole of electron. So moles of Pb to moles of electron. And then Faraday's constant converts moles of electron to coulombs. And then current converts coulomb to second. You're done. Like that. I did not put any numbers. We're just practicing here. But once again, you've given grams. You can't do anything with grams. So the first conversion is the molar mass. Okay? Molar mass is 207. So 1 mole is 207.2 grams. So you're done. You need 3 things. This is from the half reaction. Half reaction tells you that 1 mole of lead requires 2 moles of electron, or produce 2 moles of electron. Doesn't matter. The ratio is 2 moles of electron to 1 mole of lead. And the next one, okay, is your Faraday's constant. Faraday's constant converts moles of electron to coulomb. So 1 mole of electron is 96485 coulombs. And the last one is the current. 5 ampere means 5 coulombs per second. So this is your answer. Your answer has everything canceled out except seconds. And you're going to end up with how many seconds? I don't know. How many seconds? 18600. 18600 seconds. You can change it to minutes, hours if you want, but that is your answer. Okay? So when you do these kind of questions, it is stoichiometry. It has nothing to do with electrochem. You just have to understand that 5 amperes means 5 coulombs per every second. Coulombs to mole, you need Faraday's constant, moles of electron. And moles of electron to lead, you need half reaction. Using those 3 things, you can do very good stoichiometry. There's 2 points right here. So 1 point for the final answer, and 1 point for the work. You gotta have work. You can't just give the answer, right? Okay. So that's question number 5. Let's do 6 and 7. Okay. Any questions on this, guys? Okay. So again, ampere. 1 ampere means 1 coulomb per second. 1 amp of current can kill. Yeah. Okay. 0.1 amp is lethal. So if you have 0.1 coulombs of charges going through your body, you'll die. So 1 coulomb is a lot of current. Is 10 times more than lethal current. Okay. So the current that usually we're dealing with are quite small. Okay. All right. So next one is KSP question. Solubility product constant, KSP. So, they're trying to cover everything, and the emphasis is on question 1, 2, and 3. But here's a KSP one. Okay. Remember, when you deal with KSP, your X is called molar solubility. And it has to be in moles per liter, or molarity. That's the unit for X, not in grams per liter. It has to be moles per liter. KSP is equilibrium constant, right? The bigger the KSP, the more soluble is the precipitate. The smaller the KSP, the less soluble, right? But technically, you got to solve for X. X is called molar solubility. So let me write that out just to remind you that X is called molar solubility. The larger the X, the more soluble. Molar, not molarity, molar solubility. and it has to be molarity, has to be moles per liter. Bigger the X, more soluble. So you actually have to compare X, not the KSP. This precipitate has a KSP 10 to the negative 10, right? 1.8 10 negative 10. So how do you do part A? It's icebox. So your work could be icebox. You start with a solid, dissociate according to KSP into Ag plus and Cl minus. So your icebox does not care about the solid. You put 0, 0, minus X, plus X, plus X. Then you can write down the KSP is actually equal to X squared. 1.8 10 to the negative 10 is equal to X squared. So solving for X means you're solving for Ag plus. I'm solving for X. Okay, square root on both sides. You'll get the answer for X. Okay, what do we get here? We got 1.3 10 to the negative 5. And this should be 2 sig. The unit is moles per liter or molarity. That's it. This is 1 point. Actually, there's 2 points right here. Crazy. Okay, all right, 2 points. So 1 point for the answer, 1 point for setup. Now, it is actually a good practice to write down the KSP expression so that it's part of the work. I should have done that, I'm sorry. So write down the KSP expression, then write down KSP equal to X squared. Okay, so 1 point for work, including the KSP expression, and 1 point for solving for X, the answer. So always write down the KSP expression. Can you guys always do that? Okay, I should have done that. Okay, part B. Okay. So this is the part A is the molar solubility of silver chloride in water. However, part B is not in water. Part B says, what if it is in seawater where Cl minus is 0.54? What would be the X? So this is common ion effect. You just do your icebox instead of putting 0, 0. So I'm doing entire work, identical work one more time. Your KSP will not change because you're not changing temperature, right? Unless you're told. Temperature is remained constant. Yikes. And this one here. So instead of put 0, 0, you put 0 for silver, but Cl minus is 0.54. That is the difference between putting this solid in fresh water versus putting into seawater. So now you do minus X, and plus X. So this is X and 0.54 plus X. So your KSP, you have to approximate this. You don't have to test. You drop off plus X. So you just have 0.54. So 1.8, 10 to the negative 10 is X times 0.54. Solving for X, which is your Ag plus, which is your molar solubility. Just solve for X, okay? So 1.8 10 to the negative 10 divided by that is 3.3 10 to the negative 10. Moles per liter or molarity. And that is the final answer. So part B is 1 single point, okay? B1 is 1 point. So 2 points for A, B1 is 1 point, B2 is 1 point. Total 4 points again. And now they want you to explain why your molar solubility drops so much. Remember, before, when it's in fresh water, it's 10 to the negative 5. Now, in salt water, it's 10 to the negative 10. So you are not soluble in salt water. So this is the common ion effect. You just have to talk about Le Chatelier, common ion, doesn't matter. The presence of Cl minus pushed equilibrium to the left. So cause more precipitation and therefore decrease solubility. So you want to talk about something along those lines, common ion effect or Le Chatelier's, okay? So the presence of Cl minus, let me just type it out. Okay. This one. So pretty easy, okay? Again, the presence of Cl minus is going to push equilibrium left. Shifting to the left decreases the solubility. When you shift left, it's precipitation, right? Okay. So the presence of Cl minus, this is called the common ion effect. I love to hear that word. So if you remember to call it common ion, call it common ion effect, okay? Pushes equilibrium left. I'm just lagging. So shifting to the left means more precipitation results in lower solubility. More precipitation results in lowered solubility and smaller x. The goal is y-x is smaller, right? Smaller molar solubility, okay? So instead of saying x, I'm spelling out what x is. X is called molar solubility. That's the name for x. Alrighty, that's it. So 1 point for being able to explain common ion effect effectively, yeah? So please give yourself the points, total out of 4. Let's look at the last question, question number 7, okay? Alrighty. So what else hasn't we covered? We covered everything. Let's look at what number 7 is. This is the mass spectrometer, right? Remember it fragmentized the mass because they're different isotopes. So this is mass spectrometry, okay? And let's see what they want, okay? Okay, let me copy and paste this one too. This one looks like there's a lot of stuff here. Let's not copy and paste this one. I'm just gonna read it, okay? Let's just look at this. All right, so let's look at the question. And sometimes we look at the time and say, oh, I have plenty of time left for question number 7. That's a good sign, right? Okay, you wanna make sure you rush through the first 3 questions, but not so rushed that you have like 30 minutes left when you don't know how to answer question 1 and 2 and 3. So then you want to go back to question 1, 2, and 3 and do them again more thoroughly, change your answer so that they're more complete. Okay, so let's look at this one. You got a new element with atomic number 116. Okay, so it's named LV, like Louis Vuitton purse, like all Asians love, right? So this is the LV element. Okay, so Livermorian, whatever that is. Yeah. So 116. But before I read on further, I actually want to check my periodic table. Where is 116? Because knowing where it is, group 1, 2, 3, will help me, right? So I'm going all the way back to my periodic table, which is not a good idea with this lagging. So all the way in the beginning. So I'm going to look at the periodic table for a sec, yeah? And knowing which group it is really helpful. So that's what you want to do. How do I rotate? Rotate. Here. Okay, so where is 116? Yeah, because this one, okay, 116 is right here. So do you see it's in group 6? It has 6 valence electron. Okay, so there's so much thing you can write about this, but I want you to know it's group 6. And if you look at the electron configuration, remember n equal to 1, this is 2s, 3s, 4s, 5s, 6s, and 7s. Okay, your S and P is always the same number, okay? So if this is 7S, this must be 7P. And your D is always 1 less. So this would be 60. And this is 4F and 5F, like what we did before, okay? So remember, S and P always have the same principal quantum number. The energy level is the same. So this is actually right here is 7. This is 7P, okay? So you can also do this way, 2P, 3P, 4P, 5P, 6P, 7P. So 7P, 1, 2, 3, 4. So 7P4, just like oxygen, right? 2P4, sulfur, 3P4 is group 6, has 6 valence electron. That's where LV is. Okay, so with that in mind, we're going to go back, okay? So rotate it, back to free response. Yeah, next time I'm going to open one up because this one just is crazy to do this. So the last question, we're back here. All right. So this is group 6, okay? So it's radioactive for sure. Short-lived, very short half-life, large rate constant. Chemical property is group 6. What is the electron configuration? All right. So that would be that, right? So the electron configuration, don't forget the F. Okay. So you got to use noble gas. Let me just open one up, periodic table. Yikes. Do this. Out here. I need the table. Close this. Let me just open the periodic table from somewhere. This is AP Chem, AP Chem. Let me use one of the AP tests table. For some reason, I always Google 2009. I don't know what happened in that year, but 2009, yeah. This is when last recession was over. Okay. 2009, let's look at the periodic table. So make sure we know how to write this, guys. This is electron configuration. It's not going to ask you for the complete one. You're going to be sitting there writing for like 5 minutes. So use the shortcut. Okay. So do you see that LV is not here because it is LV is right here, right? So you want to use the shortcut. That would be noble gas radon, RN. That's your beginning point. Okay. So number 7A. So LV. So you begin with RN, and then what? Okay. Then we already kind of mentioned this, right? You have to look at. Let me move the periodic table up a little bit. Okay, there we go. Okay. So again, you start with RN. This is 7S, but 7S you got to go down to 5F. That's the part people will forget. Okay, because you skip. Then you come back to 6D, and then you do the 7P, 7P1, 7P2, 7P3, 7P4. So this is the LV. Okay, this is the 7P. So once you put that all together, then you got your answer. So this would be 7S2, 5F14, 6D10, and 7P4. That's the answer. So you have 6 valence electrons. The highest S and P electrons are the valence electron. That's it. Yeah. So if this is group 6, like oxygen, you would expect against 2 valence electron to become 2 minus. So if you asked what kind of ion does it form, will be LV2 minus, just like O2 minus, just like sulfur 2 minus, right? Because it's group 6. So it's going to behave like a negative 2 minus. Okay. So anyway, that's not what the question is. It's just electron configuration. Okay. So finish it. And let's look at next one. Is my the test back here. Okay, what is according to the periodic property, what is the most likely formula for a product for a reaction between LV and hydrogen? Okay, well, it's just the same way like H2O. Hydrogen and oxygen is H2O. So what do you think is with LV? Will be H2 LV. Again, the reason is because LV is 2 minus, just like oxygen is 2 minus. So the answer is H2 LV. So super easy. So 1 point each. Okay, and we're almost done. Okay, let's look at the next one. Okay, next one, we're looking ionization energy. So periodic trend. Okay, ionization energy increases as you go up a group because there's less electron shielding. Ionization energy increases across the period because of the greater nuclear charge, right? So let's see what we're comparing. We're looking at PO. The first ionization of LV is expected greater, less than, equal to. So you got to look at PO relative to LV. So let's go back and look at the periodic table. PO is right above LV. So you see that if you recall, the LV is right below PO. This is relative position, yeah? So it's up and down. So that would be electron shielding effect, right? The electrons for PO is much closer to the nucleus, is less shielded, so it's more strongly pulled in, higher the ionization energy. LV is further, the valence electron for LV is further from the nucleus, is more shielded, and is lost more easily, lower the ionization energy. So it's up and down effect, right? It's nothing to do with nuclear charge. Don't talk about nuclear charge here. When you do up and down, talk about electron shielding, the distance. Okay. All right. So that is essentially how we're going to answer this question. So let's go back to this. Okay. And also I need to get rid of this. Ooh, to navigate this is not easy. Yeah. So let's look at this. So is this PO ionization energy expected? Is the first ionization for LV expected to be greater than less than? So it'll be less than. Okay. So part C. So PO is up here. LV is down here. So we're asked, is the ionization for LV? So LV, the ionization energy for LV is less than that of PO, okay? 182, okay? So justify your in terms of Coulomb's law. So you gotta have Coulomb's law. Coulomb's law just means the attraction between positive nucleus and the valence electron. Justify, right? So you gotta mention some kind of Coulomb's law. Justify, okay? I'm just gonna write it out. Okay, so why? Okay, so you want to say that the valence electron, because that's ionization energy, okay, for LV is further away from nucleus. On the test, you got to say then that of the PO, right? Okay, let me just write it. Then that of the PO, okay, and are more shielded, okay, than that of the PO, right? Okay, this means that the Coulomb's force, so the force of attraction, Coulomb's force between the positive nucleus of LV and its valence electron is weaker. Okay, than that of PO. Okay, so this comparison, I guess, grammar-wise, it's kind of annoying because you got to keep repeating the stuff that you keep saying. Yeah, maybe there's another way to say it. Okay, so you can say that. Okay, the Coulombic force is between. So the Coulomb's force between the nucleus and valence electron for LV is weaker than that of PO, because LV valence electrons are further and more shielded. So that's probably the better way to say it. Valence electron for LV are more shielded and are farther from nucleus. So I would actually prefer this way. Yeah. So so you just correct yourself as you write answers. Sometimes you write an answer, you feel like this grammar sucks. Yeah. They'll know you're Asian. They'll give you points off. So you want to make sure you write it in such a way that at least is grammatically somewhat correct, right? So Coulombic force between the nucleus and valence electron for LV is weaker than that of the polonium. Why? LV's valence electron is farther, right? And is more shielded than that of the PO. I have some corrections I have to make here. Yeah. Okay. So, but that you get the idea. Okay. So you can perfect it. Last one here is the isotopes right here. So that's what this mass spectrometry, right? It's going to scatter the isotopes and spread or split the deflect isotope based on the mass. So here, I'm looking at this, I see 3 isotopes. Yeah. So do you see the 3 isotopes? Because one is 291, and the other one is 292.2, 292.3. And then how do you find the average? Average is the one that reports on the periodic table. So you just do the percent times mass, percent times mass, percent times mass. And they want to kill you with 3 sig fig. So they just do that then. Okay? So 20% means 2 atoms. So 20% is 0.2 multiplied by 291.2. Okay? Plus the next isotope is 30%. So that will be 0.3 times 292.2. And then the next one is 5, so it's 0.5, 50% is 293.2. You do everything on calculator, and that's your answer up to 4 significant figure. You're going to get 292.5. Okay, so that's the answer. So 1 point for knowing how to do average atomic masses. Percent times mass for every single isotopes. Add them together and you got your average. All right, 292.5. So I'm not going to put that on the answer key. So is that okay? It's not very common that we finish early. Can you please add up all your points? I'm going to give you the scoring here. So for this particular test, okay, and because you don't have multiple choice, you could use the multiple choice from before, okay? So it's out of 100 points. That would be, sorry, that would be multiple choice, okay? Plus, so multiple choice, you should have 60 questions, right? So they're actually converted, yeah, to 50 points, okay? So you have 60 multiple choice, they'll do a conversion to 50 points. And then here you have, what is this, free response, right? So your free response, how many points was that? So 10, 10, 10, that's 30 points. 4, 4, 4, 16, that's 46, okay? So you have 46, but they want to convert to 50. So they will times by 50 over 46. So you get also 50 points, okay? So again, like that. So the multiple choice, they will times by 50 over 60, yeah? That's the conversion. So you get 50 points, 50 points. So the total, the highest score you can get is 100 points. Okay, so again, this is, I think I'm lagging here. Oh, there we go. Okay, so again, the multiple choice, which we don't have, you have 60 multiple choice question. Every question is less than a point. So 50 over 60. That's the conversion. So you get 50 points for all the multiple choice. Free response, FRQ, you have 46 points, but every point is more than 1. So it's times 50 over 60, you get 50 points. So if you get 79 to 100 points, you get a 5. So this is the AP score based on this. And so that's like, if you get 80% is a B minus, but that is a low 5. So if you go from 64% to 78, 64% to 78 is a 4. So if you get a C on the AP test, it is a score of 4, okay? And then for 3 is 44%, starting to get a 3 to 63. That's a 3, okay? So the rest we're not going to look at. But so your goal is to get overall multiple choice and free response combined to about a B minus. So like 82 to 85 will be a solid 5, okay? So that's where you're at. So right now, for simplicity, why don't you just add up your multiple choice total? Can you give yourself out of 46, right? And then you can get a rough percentage to see if you did well, just based on free response, whether you had a 5, 4, or 3, right? So can you add up all your points? Because office will ask you for that, okay? So that's kind of how so your goal is always to get like 82, not 80. Sometimes I see 82 is a 5. This one happened to be 79. Is the distributed test, right? So they normalize it based on everybody taking it. So they will give you a standard deviation. So within certain standard deviation, you have 5. And that equivalent to 79 to 100. Sometimes it's 82 to 100. So you never know. So try to get a B. You'll get a 5. Okay? So overall, is it not too bad, right? There's a lot of work, a lot of doing, but is everything you've learned. Make sure you spend good amount of time for first 3 questions. The suggested time is 23 minutes at most for question 1, 2, and 3. At most, okay? So don't spend more than that. You can do a percentage, you can figure it out how much time you need, okay? So again, they say about 23 minutes the most, and then 4, 5, 6, 7 is about 9 minutes. So if you do it quickly for 4, 5, 6, 7, you save a bunch of time for the harder question 1 and 2 and 3, yeah? And free response, you can use calculator, multiple choice, no calculator allowed, all right? So please give your score for office and post them on Google Classroom if you're at home, and I'll see you guys next time, yeah? And one more thing before. Now, after this coming week, you have spring break. Please come in for 2 additional days during spring break because we will ask you to take a full test. So that way we can score your test and figure out what scores you have. So that way you get a better picture. You know, after the spring break, you have 2 more weeks before the actual AP. So there's still plenty of time, guys. Spring break is the key. If you suck right now, time to pull up your grade. AP Chem is not hard. You down and the things are always so. In for spring break, 2 extra days, please. Yeah. All right. I'll see you guys next time. Bye, guys. Take care. Bye.